at most, and then I'll give you some time on the computer, guys. Maybe even less than an hour. I'm sick of my own voice. All right, so what do we do when we cluster, right? Obviously, we have to get our data and sample selection, work out why we're clustering. Variable selection is important in clustering in real life, right? People don't tend to do cluster analysis on a very big data set. I'll talk about that. Then you want to do your graphical exploration, right? How many clusters should you have, or would you expect to have? This is particularly important. If you can come up with, you come up with your ordination, your graphical exploration, and you can see 3 distinct clusters, then you would probably come up with a clustering solution that will come. You want a clustering solution with 3 clusters. Let the computer work out which falls into what. What I've talked about, or what I ended with talking about, is the importance of standardization. Right? Are the variable scales comparable? Because if they're not, then we've got a problem. Right? Those variables with a great deal of variation, right, are going to be weighted a great deal more. Those things that are very, very small variation, they're not going to be weighted as much. So if so, do we have to standardize or transform the variables? Transformation, we won't get into this a great deal, but it may actually help with the shape of clusters. So variable reduction, you need to ask yourself, well, should I be analyzing all of the data that I have? And typically, what we have are 2 problems. One is irrelevant variables, meaning that that variable is not useful at all. If you have some irrelevant variables, then it's a variable that is not useful or interesting to whatever solution you come up with. Right? It doesn't matter what level it is. It doesn't influence what the thing is that you're interested in. Right? So this graphic is sort of showing like this variable here didn't influence the effect of that on that. Right? It was completely irrelevant. It always had the same shape, regardless of what level that was. Redundancy occurs, it's far more common, right? And that's when you've got correlations between your variables, your input variables, right? What happens if you have correlations, multicollinearity in short, right? You've got a whole bunch of x variables, and actually these groups are telling you pretty much the same sort of thing. You have a degree of redundancy. And this is, as we know, this is a big problem in regression, right? So irrelevant variables, we'll talk about irrelevancy here. You want to get rid of the irrelevant variables if you can, right? Obviously, they can be eliminated in regression type scenarios based on the dependent variable, but we don't have a dependent variable, so you kind of end up using your subject knowledge to work out what's important, what's not. Right? It's simply because it's a method of data dimension reduction. Right, and you don't want to have irrelevant variables in there because it'll just add noise to what's going on. You want a nice, clear signal at your cluster analysis. What are the differences between my clusters? Well, if you've got one variable, these things are quite different from one another, but in one variable they're all the same. Well, it's sort of just muddying the waters. Redundancy, however, right? This idea that you've got multicollinearity. That is a problem. And what you can do, what we won't do, well, I'll give you guys a lab, but it's not a lab that you're expected to do during the block itself. But the lab is basically about prop varclass. And what prop varclass does, essentially, is it does a cluster analysis on the variables themselves. Right? And it finds out, hey, look, I've got all these variables here. Protein, this is I think it was, what was the actual data set? The amount of pizza, you know this data set, of course, yeah, the pizza data set, right. Yeah, the amount of protein, carbohydrates, and moisture, etc., in these things. And you realize that, in fact, if you plot a scatter plot of all these variables, a bunch of them are related to each other, right? Those things with high protein also tend to have a high carbohydrates, etc., etc. Right? So you can actually do a cluster analysis based on this, and say, hey, look, I actually tend to end up with 3 clusters. Yeah. What I might want to do, well, what could I do? I could do a PCA if I wanted to, and just plot the principal components and use that in my predictive model, if I wanted to do that. But the problem with doing that is, of course, your principal components as input variables are not intuitive to people. They're linear combinations of all of your variables, right? So particularly in industry, where you want nice, clean answers, you might just want to choose one representative of a particular group. These things, they're all roughly telling you the same sort of thing, right? If you look at the correlations with its own cluster, they're very high, right? These are all correlated with, these guys are correlated with each other. These guys are correlated with each other, right? So what you want to do is choose a variable that is highly representative of its own cluster. In other words, it has a high number here, but very different to the other clusters. So choose, let's say the next closest cluster to it, you want to choose a variable that has a very low R squared there. And in fact, what they do is they look at the ratio of these things, right? And you work out the 1 minus R squared ratio, and you choose the lowest number. So in fact, for this cluster, this particular statistics is choosing carbohydrates as the best candidate, because although it has a moderate correlation with the next closest, it's got a very good correlation with itself, with the actual cluster itself. So you tend to choose, well, one method is to choose that value with the one value for each cluster, one variable within each cluster that has the lowest 1 minus R squared ratio. Right? So you choose carbohydrates, you choose moisture, and you choose fat, right? Right? The idea being that these 3 guys are quite different from one another, but representative of the other variables that make up its own cluster.
Is there a particular reason they've done 1 minus R squared and pick the lowest?
1 minus R squared instead of the direct ratio? No, I don't know actually why they've done that. Probably because it gives a statistic that is going to be bound within some sensible numbers, but I don't know specifically. I mean, you could look, there will undoubtedly be some theory behind it. But.
How is it different from factor analysis?
So, say again, sorry?
How is it different from factor analysis?
So what is that? So that's a very good question. How is it different from factor analysis? I'll throw that over to you guys. What is your factor in a factor analysis? Is it a single variable? No, it's not, right? It's like a PC. It's a combination of your other variables. So a factor analysis, you're finding you're not choosing a single variable, you're defining a latent variable and saying, hey, look, these guys here, protein, ash, and carbohydrate, I'm trying to come up with something that sort of signifies what these things are. I don't know, meatiness. Maybe it is a method of these things are actually all very similar because it's amount of meat or something within the pizza. I just may pull that out my ass. I don't know yet. But maybe it is, and that's the latent variable itself. You worked it out that that's the amount of meatiness of the variable. This might be fat and sodium. Well, these things are not good for you. Badness, you know. And so you've got some latent thing that is actually a combination of these things, right? But you have redefined it and saying, hey, look, this particular factor is, hopefully you can come up with a name that describes it. So here we're just choosing one particular variable. You know exactly what it is, so it's nice and clear, right? It's not a latent construct, it's something you directly observe. A factor analysis, you're creating latent variables that is a combination of these things.
No, sir. And the R square is used residual to get the R square. So what's the residual here? In normal linear regression, the R square is the y.
How well, basically, it is how well it's fitting, right? How well is your variable fitting?
Yeah.
With the cluster itself.
Yeah.
Yeah.
Yeah, but it's when we calculate it, is the the response and we predict and the minus and the summary and to SST and SSE to divide them. But here, what's the y? Because we don't have the y.
Yeah. Well, here we can, and that is going to be the square of the correlation. Right. Well, if you've only got two variables, then it's simply one regress on the other, and you know it's simply your correlation between these two things. Right. So this is actually going to be the square of the correlation. So if you've only got two, it's very easy to calculate what it is. You can think it intuitively. If you've got more than two, how do you calculate your R squared with your own cluster? I don't know. That's a good question. It may be something like the average of that variable with that one and that one, but I don't actually know. Yeah, but it'll be something along those lines, or of, let me think. Yeah, I don't know, sorry. Yeah. It may well be the average, the median of all of the particular values, and you look at each observation. There's a variety of ways you could do it. I could think of it, describing it.
So when it says next closest to,
As defined by cluster analysis. So we're sort of delving into it maybe in greater depth than I want to do, simply because we haven't actually talked about what the cluster analysis is doing. But essentially what you end up with is, let's say we've got three clusters like this, right? You have a centroid for each one, and you can have a distance between these centroids, right? This is cluster one. This is the closest one to it compared to that one. So it's looking at how similar is it to this one. Right. Okay, so a little bit more than I meant to get into, but I will give you I give up a lab describing this and put it on stream for you guys just to do it in your own time, because none of what we talk about or is going to deal with that particular method, but it is seems quite useful. Okay, so we're going to spend most of our time talking about agglomerative hierarchical clustering, right? We'll spend a little bit of time talking about k-means as well. Okay, so in k-means, in partitive clustering, what you do is you choose beforehand the number of clusters that you want, right? So apologies for you data mining students who haven't done it. You're about to probably get the same lecture about k-means as you will here. Whereas with a hierarchical method, what you do is you go one direction or the other direction. Typically, with an agglomerative method, you're considering all of your data points as being different, and then you start grouping the ones that are close to each other. Right? So say, hey, look, 1 and 5 are close together. I'm going to call that a cluster. 3 is not really close to anything. Neither is 2 or 4. So this is the first cluster, and these guys are still what they were. And then these guys are considered at a slightly, if I sort of expand my level, these guys are now considered close enough that I'll lump those. And eventually, as you go consider bigger and bigger distances, right, and I'll talk about what that means, you're going to end up with one big cluster. So you can think of it as saying, hey, look, and we'll spend some time on this. I'm going to start off with what points. We'll just look at those points that are really close together, and we'll group those, right? But there are no other points that are particularly close together. And say, okay, let's think of saying, hey, look, if I look at the same distance between everything, they're all sitting on their own, right? Well, let's look at a bigger distance now. Let's say we take it that distance here. And at that distance, these guys are also grouped, and those guys are also grouped, right? And then we'll go to a bigger distance. These guys may group, those guys may group, right? And then eventually, everything is going to get grouped into one cluster, right? As you increase the distance as to what you're considering to be part of similar enough to group together, right? That's going this way. Similarly, you can go the other way around, divisive clustering, And that's starting with one cluster, and then you start splitting things. So we're not going to deal with that. It doesn't tend to work as well. All right, so the one I'm going to talk about mainly is hierarchical agglomerative clustering and k-means. Right? They are the two most common clustering methods. Right? So from here, this is your dendrogram, basically. That's what you're going to end up with. You can then choose the value that you think, the number of clusters that you think is correct, right? Based on your analysis. Here, with partitive methods, we don't have this hierarchy, right? It is problematic. The hierarchical clustering is probably the most common method, except with pretty big data. But if you get it wrong, if it gets it wrong early on, those errors do tend to flow through, so it can be a bit problematic. But to use k-means is very fast. A lot of people use it, very fast, good with big data. But you have to know the number of clusters that there are to do the analysis. And we'll talk about that. K-means is good. A lot of people like it because it's fast and because it's intuitive. Much simpler intuitively than other methods, the hierarchical methods. Okay, so this is sort of what I was talking about. So agglomerative, to agglomerate means to collect into groups, right? So we start off considering every data point as being a separate cluster, and then you start joining them together, right? You say, okay, we're going to say that at a certain distance, we'll choose a particular distances. As we increase our distances, these guys are very close together, these guys are very close together. This guy was still very far apart at this particular distance. Right? And eventually, these guys are going to get joined, and then eventually, the distance that you get is so big that everything is one big group. Right? Divisive is going the other way around. Right. And here I say that we don't use divisive clustering in the course, but in fact, ProgVarClass does use the divisive clustering. I won't get into the details too much. Essentially, it does an eigenanalysis on each of your clusters, and it looks at the second eigenvalue. And because what you're trying to do here is trying to represent your data, hope that your cluster will just be representable just in one dimension. If you can represent that in one dimension, all your variables in one dimension, then there's no need to split it. Right? There's really only one variable here. But if in fact you've got a big second eigenvalue in the analysis, then you need more than one dimension to split it. So really you kind of need two variables to split it up, and that's sort of one of the criteria it could use to determine whether they're splitting something. But once again, that's actually outside the course itself. I just throw it in there because it is quite useful. Okay, so scale. Got two plots here, right, with 4 data points. How would you group these observations in each plot? I think most of you would say, hey, look, these guys are similar to one another. These guys are similar to one another, right? I'm going to say there are 2 clusters here, one here and one here. Similarly, these guys here and these guys here. Right? Is that what you would do? Right? These are the same data, just plotted on different scale. So in fact, there's no difference between these plots. So wrong, unfortunately. It's a bit problematic. And if you look at the scale here, we go negative 0.1 to 0.1. Negative 0.01, negative 0.01, negative 0.01, negative 0.01, right? So we sort of swap the actual utility of these things. So do be aware that, visualizing things, you want to make sure that all your axes are on a similar scale, so that you're not just, if things look together, to be close together along one axis, it's not because that axis is a completely different scale than the other axis, right? So some distance measures, in fact, are actually sensitive to variables having different scales. If you're a biologist, Bray-Curtis is a very common distance, and that one is sensitive to different scales. So combining one variable which measures affluence, sort of money, on a scale of 1 to 10, with, say, income measured in tens of thousands is problematic, and this is why we want to standardize the data typically. Standardization is typically done, right? Usually there's a, the only time you wouldn't do it would be if your variables are measured on a similar scale and the differences that you see between the variables are actual real differences. The differences in variation that you see between the variables are actual real differences that you want to use to drive the clusters, right? That would be really be the only time I can think of where you wouldn't want to standardize. So typically you're going to standardize your variables, whether it's dividing by the standard deviation, right? So that all of your variables are in standard deviations, right? You might want to subtract the mean and divide by the standard deviations, so all your data is centered at 0 and measured in standard deviations. Right? That probably means that most of your data points, all of your variables are going to be between -2 and +2, right? Remember, plus or minus 2 standard deviations is going to cover about 95% of your data, right? 99% will be covered in 3. So that's still going to be problematic when comparing it with your binary variables, though. Right? Binary variables are going to be 0, 1. 0, 1. So typically, in fact, people might want to use something called range standardization, which is basically you take your minimum and your maximum values and you ensure that your values then are the 1 is the maximum and 0 is the minimum, and everything else falls in between those two things. So standardization may actually, you might have well separated groups, right? But after standardization, it may not be so well separated, but that's just the way it is, right? If in fact these guys, they look nice and separated, but that's because they're on completely different scales, it may then just be dominated by one variable. So Adam wrote these notes, but I kind of disagree with the point of it. So although standardization may have obscured your two well-separated groups, right, then really they should be similar to one another unless there is some reason that you haven't standardized, really. Right, so standardizing is done usually through the proc standardize procedure. From memory, proc cluster has an option where it will standardize automatically as well. But don't quote me on that. So turn off that tape. Guess it's wrong. Right, so there are a whole bunch of different standardization methods. Right, I won't get into all of these things. But typically people use the range standardization or standardizing by the actual standard deviation is typically the way that they go with. Okay, so we'll talk about this. We've already talked about this. So a quick poll: if your variables have different scales, right? What do you want to do? You want to you usually do not need a standardization to standardize, right? B, the standardization doesn't matter. It's only important that you standardize. C, it's important that you standardize, and your choice is actually important. Well, C is the one we have to think, right? So hopefully you're going to go with C. It's the only way the answer.
Question on that, what you just covered with the skewing the clustering.
Yeah.
Is he just talking about just the plotting and the visual representation of it, or does it actually have a real numerical impact?
No, it has a real numerical impact on the clustering itself. It's a good question, right? Whereas here, because if you're standardizing the data, these things are then going to look, previously, you might actually see the cluster analysis would actually have these points being quite different from this group here. Right, well, let's go up a slide, because this is basically the same slide, right? These guys would say, hey, look, this is one cluster, and that's the actual solution you get. Whereas after standardization, it's not clear to the algorithm what's different and what's not different. Yeah, so it actually has an impact not just on the visualization, but on the clustering algorithm itself.
The top one's blue and the bottom one's orange.
Yeah.
It's the same data.
Yeah, well, that happens because the cluster solution will still give you clusters. It's just, you know, what were those clusters? Well, here, if you did the clustering solution, you did this, and that looks sensible, right? Here, well, is that a sensible solution? Clustering it, that is one group, and that is one group. Maybe not. Maybe not.
Yeah.
Probably.
Because you can also change the scales of that vertical axis and the little bit.
Oh yeah, look at that. It has been changed. Yeah.
So.
That's because of the standardization, in fact, as well. Yeah.
Are the yellows the same category?
Yeah. Oh, they're just two categories. There is no same or different category. They are just category 1, category 2.
Can you explain how that it shifts from one to the next?
Yep. Basically, you've just done a cluster analysis here on this data, cluster analysis on this data, right?
Oh.
In both terms, both examples, you've just asked for a 2-cluster solution.
So they're not the same points.
They're not exactly the same points. No, there's one is this is the same data, but this one has been standardized. This one is unstandardized.
They've clustered different points. That's what I mean.
They've clustered the data prior to standardization, and then that same data after standardization, run the cluster analysis again.
I think the question is, are the yellow points in the first one the same as the
No.
second? I think that-
Right, yes.
It's something like that.
Yes, that's right. You're absolutely right. They're different points that have been clustered.
Okay.
Yeah. So that was sort of the point of it. You end up with a different clustering solution, different points. Yeah. Standardization shouldn't actually shift the relative location of points relative to the other points per se, particularly. I mean, a point at the bottom should still be at the bottom, typically. Okay. So we'll talk about the k-means clustering solution, I think, and then I'll get you onto that first practical. So the k-means clustering solution is nice because it's fast and it's very intuitive, right? The problem is you need to choose k. You need to choose how many clusters you want, right? So you're going to choose k, and then the algorithm is going to classify your objects into those number of classes, right? The algorithm actually just generates a random starting point, typically, and it does it iteratively, but it is fast. Right? Hierarchical clustering is slow, order n cubed or n squared, and so it does run into some problems if you've got really big data. Got a lot of data points. It's problematic. I've got a better set of slides than that, I think. Here we go. Okay, so what do you do? Well, we know that there are, here's our data points, right? We're going to pretty much randomly select our centers. So we're going to set it and say, hey, look, I wanted 5 clusters. I have to know how many clusters I want, right? So I'm going to say, I'm going to basically choose 5 random points on that. It actually tends to be very robust. K-means irrespective of your starting points. You might get some slight differences. 5 random points, and these are my cluster centers, right? Then I basically look at the distance between all the data points. So look at the distance between all the data points and all the centers and assign it to the closest one, right? So these data points are all obviously very close, closer to the blue center than anywhere else. These points are closer to the red center than anywhere else. All of these data points are closer to the pink center than anywhere else. You'd think actually that was closer to the red, but it is what it is. Orange and yellow. Okay, so that's great, but that's not your final answer. Because, of course, now that you've assigned these points to a class, you can recalculate what the actual center is of those data points. I can now actually calculate the centroid of the blue points and calculate the centroid of the red points, etc. Right? So I can update my cluster centers. Right? And then, once I've done that, I've basically shifted the center, and I can look again at the data points and reassign it as according to where these new centers are. So I do this lots and lots of times until eventually, see, the centers are very subtly shifting, but the actual classification is not. So I reassign these cases over time, and eventually they're not going to change. That's what they call the method. The algorithm has converged. There's no change in your solution. It's come up with your answer, your final answer. And that's your solution, as simple as that. So you can see,
How does it come up with, so that's step 2, select K cluster centers? How does it? do
random.
that per
Well,
step?
there are different methods, but we could choose. Typically, it's just a random positioning of points, right?
So, does it kind of matters specifically where it puts that point in the first instance? And then
You'd be surprised how well it converges anyway,
Okay.
right? Because what happens is if we have a data point that started, say, a centroid that started down here, it might only grab a couple of points here,
Yeah.
but the centroid moves very quickly up to here, and then it starts shifting across.
Yeah.
So what happens is you tend to end up with sort of homogeneous groups, irrespective of the starting point, right? So it's a good question, but that's what happens. It tends to give pretty robust answers. So it is intuitive, right? You can easily explain that to somebody how it works. It is really fast, easy to implement, and it comes up with reasonable solutions typically. Best of all, one of the good things about it is you can very easily assign a new data point to a cluster that you've got, right? If I have this solution here, end up with this solution, new data point comes in, bang, you can very quickly work out which center it's closest to, right? You're looking at the distance, right? So you can see why the distance matrix is important. Just choose that particular thing and categorize that new data point very easily. Right, so its main problem some people think is that you have to specify K in advance. You need to know how many clusters there are, when often you don't know that. It may not be as big a problem as you think. People will often run a whole bunch of different Ks and see which one seems to give sensible results. More problematic really is that it's sensitive to outliers, and that it really tends to give good responses when the clusters are nice sort of convex shapes like spheres or ovals. Right, so if you have some funky shapes in your data, it may come up with some what are pretty arbitrary splits, right? So it's a little bit sensitive to the initial starting point. So you'll come up with different solutions. But to be honest, this sort of unsupervised method is a bit of a guessing game anyway, cluster analysis, right? You should never believe your cluster. It's just an approximation of what's going on. As obviously, you have to be able to define a centroid, right? So categorical data, you have to have, well, it's going to be true of all your clustering methods. You have to come up with some way of making the scales standardizable and measurable, so you can include your categorical data in there. So the solution that you get, and what we have here is essentially some sort of loss function, and a loss function is difficult to define with an unsupervised learning method. We have to say what is best in some way. There are a variety of ways that we can do this. None of them are ideal, and I'll talk a little bit about them. But obviously what you want to end up with, the loss function is typically, hey look, the variation of my data within my cluster is very small relative to the variation between my clusters. So that sort of ratio is probably going to be important on here, right? And you want to find something that is where the ratio is going to be extreme, right? So you may not get the most extreme value of that particular that loss function just at given a particular starting point. So just like MDS, right? You might come up with different solutions if you run it a variety of times. Okay, so people often just essentially look at 2, 3, 4, 5, whatever groups, and choose the one that they think is the most sensible. Certainly, within industry, I think it's sensible to say, or it's common to say, that they know how many clusters they want, how many groups they want, right? If you don't have a marketing budget to just split it into 12 different segments, right? They say, okay, I want to split my data into two or three different clusters. We'll see what the data say, but it's either going to be 2 or 3 because A, that's what the budget is, and B, they have some sort of a priori knowledge, the domain knowledge of what's going on. Right, so actually, in industry, it's pretty common to have a pretty good feel for what K is going to be anyway, or what they're interested in. In business, it's probably pretty rare that you're trying to cluster into lots and lots of different groups, right? I mean, maybe that's changing a little bit with bigger data, and the whole idea of personalization. And clustering is trying to personalize your marketing towards you, right? So you need a lot of data to be able to come up with, the segment that is exactly you, I guess. Right, so what do we got? We have, you choose K, and that's going to choose, basically, it's going to translate to the number of clusters that you get, right? And there are a whole bunch of things. I'll basically talk about this as to how you choose K. But there's no right answer. Okay, that's where I'm going to stop, and you are going to do the lab or practical. Let's do the practical one at this one time. Once you've done the practical, do the lab as well, or start on the lab, which is factor analysis. I forget what the lab is. Might be clustering. Maybe do the practical. We won't do the lab yet. Let's have a look at this. It's saying protein and ash are quite different according to the PCA.
Yeah.